If we want to do some urban mining, we need information about where to find secondary raw materials in which quantities and qualities, ideally under consideration of possible future developments. This means that we have to characterize the urban mine just as this is required for geological mines. Now, the urban mine differs in some aspects from geological mines, for example, regarding the typically high geographical dispersion of its constituents and the dynamic change in their composition through, for example, technological innovations. This is why characterizing the urban mine requires a specific approach. The characterization of the urban mine in a strict sense typically consists of the following three steps. The first consists in creating a representation, an abstract model, of the system under investigation, including the definition of the scope, what are we looking at, the boundaries of the system, the relevant processes, stocks and flows, the relevant interactions with society, and the scenarios to be addressed to anticipate possible future developments. The second step is to agree on a classification system and to populate the model with data from available data sources, for example, manufacturers, sampling experiments, or official statistics, like Eurostat. The third step consists in performing scenario-based simulations to anticipate possible future changes and developments of the urban mine. In addition to this, the outcomes will have to be evaluated regarding feasibility, impacts, as well as legal and regulatory aspects. Based on that, decisions on implementing urban mining strategies can be taken by the different stakeholders involved.
In Switzerland, car embedded electronic devices are not dismantled from cars before they are shredded. However, a new proposed legal amendment plans to establish a list of car-embedded electronic devices that need to be mandatorily dismantled and specifically recycled to recover rare metals. The central question now is the following. Recycling which devices provides the most environmental benefits at the lowest cost and should thus be put on this list in priority. So let's precise our scope. We want to characterize the urban mine of some rare metals contained in electronic devices which are embedded in cars, and all that in the boundaries of Switzerland. We now need to define all the processes through which those metals in devices in cars go through during their life cycle in Switzerland. Those processes are connected between each other through mass stocks and flows. However, the interaction of our system with the society and the environment can be significant as well, through, for example, energy flows, waste and emission flows, and also money flows that are basically gains or cost of specific processes. So now we want to give some flesh to the model. So the first step would be to classify our subject in order to obtain meaningful and relevant results. For example, in our case study, we classify cars by their propulsion technology. The devices, the type of waste produced by each process, everything in fact can be categorized as well, following the same principle. We also need to populate the model with relevant data such as electronic devices composition in rare metals, how they behave going through each process, etc., etc. So data regarding interaction with the environment and society is also needed, such as the energy need or global warming potential of some processes or market prices of secondary raw materials, for example. So in short, every element of the model needs to be quantified following this example, this logic. Evolution scenarios of all those parameters are done as well to make the model dynamic. We can now simulate the urban mine simulate it at a time t in order to characterize it. This allows us to obtain mass flows between processes and stocks, but also other flows linked to society and environment. We can then also simulate stocks and flows at time t plus delta t using the scenarios, and so simulating in the future, in the past, and so on. So now we would evaluate the results and do the actual characterization. So first, we evaluate mass stocks and flows themselves. So here, for example, we see that the amount of neodymium in accidented and end-of-life cars will increase in the near future due to rapid electrification of the fleet. We also then evaluate relevant implication of those mass toxin flows, such as, for example, its interaction with the environment or society. So here, for example, we can see that recycling certain types of electronics can reduce the environmental impact through avoided copper, while recycling other types of electronic devices can reduce the environmental impact through avoided gold mining. So, yeah, interesting results. Now, we see that this characterization provides really the basis to make decisions and to take action. So let's come back to the central question of our example. Which car-embedded electronic devices should be put in priority on the list of devices to be mandatorily dismantled from car and recycled specifically? So, thanks to our urban mine characterization, we can now provide all the elements needed to answer this question to the decision maker. An economic cost and environmental gain for the recycling of each specific device. The amount recovered of some critical metals can be also central information as well to take this kind of decision. So this study case, in fact, is inspired by a real project that we do called EVA2, and we are doing it for the Federal Office of the Environment in Switzerland. However, there are many other situations where urban mine characterization might be very useful. Imagine, for example, a municipality that wants to improve the recovery rate of some specific materials in its waste, or an entrepreneur that needs to make a business plan for a new recycling facility, and so on. In short, I would say that urban mine characterization is really a great tool to help find concrete and efficient solutions in a circular economy framework.